that switches there. And I guess share. Yes. Done. Done, done, done. Now we gotta wait for her to get back. All right, the other half is here. We can begin. And let me switch that on, that off. And position that. Yeah. And unfreeze there so you can see. All right. Here we go. Good morning, everybody. All two of you. But and the folks at home that'll be watching later, hello to you too. Today, we are going to dive into a doozy of a topic that is super critical by the time you get to calculus. This is basically all of what calculus will be about, is rate of change. Right? That's one of the definitions of calculus, is this mathematics of change. And we're going to look at average rate of change here today before getting into the rest of our polynomials, which is not polynomials, functions. Let me just clarify. The way that Khan Academy has broken things up, we're going to deal with polynomials as an expression of themselves and then get into various features of the functions as well as factoring. So that's going to come back again as longer forms, factoring polynomials. And so we'll hit all of that again. I have no idea why Khan Academy decided to put this topic right ahead of the polynomials. It is not specific to polynomials. Okay? So we're throwing this out there. We'll talk about it. We'll go through it. It's not that complicated. But just full disclosure, there's not a direct connection to the immediate thing before or the immediate thing after. It ties to everything at once. This can be used on any function, okay? So what are we dealing with here? Average rate of change. Okay, we got to talk about rate of change. So, spoiler alert, stuff changes, okay? Nothing ever stays the same. Look at this. We have a price listed. This is the cost of something. Did they tell me actually what it is? Gasoline. There we go. Price of gasoline here listed over the years. So as the years go by, 2005, 6, 7, the cost per gallon changes from 231, 262, 284. Notice there's been a general upward trend. Oh, nope, it dropped back down. Oh, then it starts growing again. 58, 368, right? So it's changing, it's fluctuating. And we want to know, this is a very common math application question. Okay, how is it changing, right? That's generally what calculus is going to ask. But we can do some algebra too to get a more general sense. We can find the average rate of change over the specified time period, right? Over the course of all of those years, on average, about how did it do, right? We know it changed rapidly some years, jumping from 284 to 358. That's a big jump. Compared to 330 to 241, that went down, right? So sometimes it goes up, sometimes it goes down. Overall, on average, about how well is it done? Has it increased a lot? Has it increased fairly steadily? These are the kinds of questions we're going to start to ask, not only in algebra, but eventually calculus. And calculus will get us something different. It will let us find the instant rate of change. It'll say, well, at this exact year, this is how it was changing. We can't get that precise yet. We need calculus concepts for that. So we're just dealing with average, right? The big numbers. This is what average rate of change looks like. You're going to look at the whole change of output over the whole change in input, aka delta y over delta x. There we go. All right. So if you haven't seen this before, Greek letter, delta, it's just a triangle, okay? And we use this letter, like many of the Greek letters, they get borrowed into predominantly physics, borrows a lot of Greek letters. Math, we also use some Greek letters in spaces to stand for something. And in this case, delta is always standing for change in. Right? When I say delta y, I mean the change in y. Right? So delta y over delta x means the change in y divided by the change in x. And this change is nothing new. You've seen this before, right? y2 minus y1, the change in the y's, over x2 minus x1, the change in x's, right? What formula does that bring back to mind? The slope. Yes, very good. That's the slope formula. That's really all this is. Except we're going to use it on something that's not a line, right? That's the freaky part. If this was a straight line of the gas prices, it would just be calculating the slope. But we're going to instead take a curve, connect 2 points with a line, and find the slope of that line now. And this is where our technological changes from this morning. We had some issues earlier. Power went out, whole big shebang. Right? Anyways, I don't have my usual drawing tools here. But instead, I want you to imagine y equals some curve there. And we are instead going to connect, let's see, I want to go from y equals, let's try 3x plus, nope, that's too much. 2x plus 1.5x plus 1. That's what I want. One hit right there. All right, so take a look at this graph. What I have here is the curve, right, that is showing the actual data. Let's just pretend this represents the actual data that we have, all right? Or it could just be itself a perfect exponential curve, okay? Except the slope of that curve is not constant. Here it's pretty shallow and it gets steeper and steeper as we go. That's one of the main useful features of an exponential, is that it gets steeper and steeper as you go. It's like, okay, that's great. But about how much does it change between 0 and 2? Well, that's where we could approximate it just with a linear line here. We'll connect those 2 points, find the slope of that, and notice down here, the slope is a little bit less on the curve, right? Would you agree that that curve there part is not quite as steep? But over here, the red curve is steeper. We go from less steep to more steep. And so on average, it's about equivalent to this blue line, because it gets to the same place in the same amount of time, as it were, right? That's what we're dealing with. We're finding the average rate of change. It's just the slope between 2 points that are on a nonlinear curve. So for this data example, gas prices, if we take the total difference from 2005 to 2012, so take 368 minus 231, you get $1.37. It went up $1.37 over the course of 7 years, which means on average, the price of gas has risen by about 19.6 cents or $0.196 per year. Right? That's the average. Sometimes it's more, sometimes it's less. We understand that's what average means, right? That's all we're doing here. It's actually not that complicated, as I mentioned. Okay, any questions so far on the concept of average rate of change? No. All right, we got some other examples, just things that would increase or change rapidly. Think about this. Population of rats increases by 40 rats per week. Does that mean Sunday through Friday, there are no rats born, and then all of a sudden Saturday night, boom, 40 more rats appear? No, right? Clearly not. They're scattered throughout. Some are born Monday, some are born Tuesday, right? And then on average, over the course of the week, there are 40 more rats. See the difference there? All right. General note. Rate of change describes how an output changes relative to the change in input quantity. This is where it becomes useful. We don't want to know just, okay, how much total does the price of gas increase? We want to know, okay, on a year-to-year basis, per year, we want to compare it to something. We get that unit rate, okay? Here is the exact same formula using the function notation, f of x notation. And it's still difference of the outputs divided by difference of the inputs, delta y over delta x. So all you need to do is find 2 points on the equation that you're finding the average of that interval. Right? It says find the average rate of change of the price of a gallon of gas between the years 2005 and 2012. Right? That's going to give you your interval. Okay, I got to find the point on the graph at 2005, it's here, and the point on the graph at 2012, it's there. Right? You'll be told this. You'll be given some interval. Find the rate of change between x1 and x2. Well, you're going to need the difference between those two. That's easy. Subtract that. Done. And then if you don't have means already, determine what the function value is at x2 and x1, right? And then subtract those. And then divide. 3-step process. So let's go through another example. Using the data in the table below, find the average rate of change of price of gasoline, I'm assuming of a gallon of gasoline, between 2007 and 2009. Ooh, different years here. Find 2007, 2009. Here's 2007. Here's 2009. I don't care about the rest of it. I only need these numbers. Right? Ignore this guy in the middle. Ignore this extra stuff on either side. Doesn't matter to me right now. So I would reverse these. I would say 2 and step 2 is easier than step 1. 2009 minus 2007. That's 2 years. So our denominator is going to be 2. And then I need to do 2.41 minus 2.84, right? Because I did second minus the first. Make sure you put them in the same order here. Right? Here it is spelled out for you. Our formula. 2.41 minus 2.81. Because 2.41 goes with 2009, right? If you want to do them backwards, you can. Just make sure you do them both backwards. So we're actually going to get a negative change in the price over 2 years. So on average, the price fell by 22 cents per year. Okay? Interesting. Notice this average rate of change is completely different from this average rate of change. That can happen, right? Because we are not dealing with a constant graph. We're not dealing with a straight line in the first place. That's why we have to call this out as a thing and calculate the average. Otherwise, we would just give the slope of the line and be done, right? It's going to be different in different places. Absolutely expected. All right, yeah, that's a decrease because it's a negative increase. That's just phrasing there. I think you can understand that part. And that's all we got to do. So your turn will be to complete these triads. Right? There are 1, 2, and 3 for you to give a try here. Right? What changes? In example 2, we're actually dealing with the graph there. This is rather interesting because take a look at this. Here I've got average rate of change from -1 to +2. Notice it's negative. Right? I could find the average rate of change from, say, 0 to 3, and that would be a positive. You could also, if you went from the rate of change between 0 and 2, that would be a straight across horizontal line here. You'd get an answer of 0. You'd say, oh, there is, on average, no rate of change between 0 and 2. Right? That's okay. Because it dipped down and then it came right back up. Right? Think of average rate of change as like how your stocks are doing, right? When you check them. The stock rate, the price is fluctuating lots, right? You've seen the stock price chart there, those giant squiggly zigzaggy things. It can't hold still. Okay, it's had way too much caffeine. But when you stop and look at the price, okay, when I bought the thing, it was this. And several months, years later, I look at the price, it's this. You're just comparing those two end points. What did it do? Totally possible that it dipped down, came back up, and you have not made or lost any money. It's the same price. Okay. So there is example 2 is basing our data on a graph. Example 3, still from a table here. Not really any different. Example 4, you can, of course, just be given the formula, right? And interval notation from 2 to 4. Square brackets, that means including. So our x2 is 4. Plug that in to find y2. x1 is 2. Plug that into the function to get y1. Right? And I think that's what you'll be doing on try it too. Yep, here's the function, here's the interval. Okay, so instead of reading from the chart, you'll have to plug and chug to get some of those values. And then number 3 is where it gets tricky. I want you to practice finding the average rate of change as an expression. Notice here, try it number 3 says, on the interval from 5 to A. That's not a number. I can't plug in and find a value for that. True, you're not going to find a value for that. Because I want you to find the general case, right? What you're going to do is you're going to come up with, look at this example here, equation of our function, interval 0 to A. So the expression will be involving A. You'll have some answer that says, hey, the rate of change is 2A, or whatever it ends up being, right? Whatever you want to find it out to be, it's always going to be twice that. Or in this case, looks like we plug in A, we plug in 0, stuff simplifies, right? Factor, divide, and you get down to A plus 3. Right? So at any point on this function, I can determine that the rate of change will be 3 more than the actual value I'm looking at. Right? On the interval 0 to 5, the average rate of change would be 5 plus 3, 8. Right? And that's kind of neat to get an expression for the average rate of change. So number 3 is the challenge question. Try it anyways. See if you can do it. Yes, the solution is available there on the website if you need to check. But I want to see your work, what you can do without. Okay, any questions? No? All right. Link to this page is on Google Classroom if you didn't find it already. So you can read off the actual problems there. Your mission today, 3 problems. 3 try-its in the green boxes. That's it.